Centre of Excellence for Particle Physics at the Terascale. We like to shorten it COE. I need to start these proceedings in the university's customary way by acknowledging the Wurundjeri people as traditional owners of this land, and in doing so pay respects to the elders past and present of the Kulin nations. So we've had an incredible couple of weeks in physics, which many of you were present a couple of weeks ago when you had all sorts of things happening with the Higgs boson discovery. And last Friday we had a panel as part of this series with really the world's leaders who are here for ICHEP, the International Conference on High Energy Physics. And then last Tuesday we had Fabiola Gianotti from CERN. She's the Atlas spokesperson telling you about what's happening there. This series was aimed at bringing fundamental physics from the very smallest at the microscale to the very largest at the cosmological and scale. So tonight, then we'll be talking about the very big. And Jeremy Mould is going to be our lecturer. Jeremy is professor at the Swinburne Centre of Astrophysics and Supercomputing, and he's also a professorial fellow here at the School of Physics. He's a graduate of Melbourne and of ANU, and following research fellowships at Greenwich Observatory and observatories of the Carnegie Institution in Washington, he moved to Arizona and became an astronomer, assistant astronomer at Kitt Peak National Observatory. In 1982, he joined the faculty in Caltech, and then in 1993 came back to Australia to head up the Mount Stromlo and Siding Springs observatories. He went back to Arizona in 2001 to become the director of the National Optical Astronomy Observatory, which position he held until 2007. He's one of the world's leaders in studying stellar populations in galaxies, which are used to determine the age of galaxies and their evolution. And Jeremy, Professor Mould, this led to a leadership position on the Hubble Space Telescope Key Project on extragalactic distance scales. So this work has led to the measurement of the Hubble parameter, which is a measure of the age of the universe. Jeremy, Professor Mould has earned numerous professional awards and honours, and most notably the Gruber Prize in Cosmology, a very high distinction in 2009 with his colleagues Wendy Friedman and Robert Kennicott for the definitive measurement of the rate of the age of the universe and rate of expansion with Hubble's constant, as I said, which is basically a measure of the age of the universe, or is used as a measure of the age of the universe. He's meticulous and has done a huge amount of work in cosmology, of which he's been highly cited. So he's a fellow, Professor Mould is a fellow of the Royal Astronomical Society and the Australian Academy of Sciences. He's served on many editorial boards, including Planning Advisory Committee for NASA, and has authored over 400 papers. So I think we're very, very lucky to have Jeremy as an associate of this university, and I'm sure you will agree that we're lucky to have him speak today. So, Jeremy, it's over to you.
And thank you all for coming out on a night when you might be wanting to watch the footy. I can promise you that if the footy's exciting at all, I'll let you know what's happening. Right now, thank you for the kind introduction, Jeff. And as Jeff said, he's director of the Centre of Excellence for Experimental Particle Physics, which has been all in the news this month. Up here I have the logo of another ARC Centre of Excellence that got up at the same time that Jeff's did. It's the Centre for All-Sky Astrophysics, and I'm part of that collaboration 5 Australian universities and a number of international partners. So, tonight's topic is Understanding the Cosmos. It's a bold title, and I hope we'll understand a little bit more by the end of the lecture. It's what we do every day, of course, and at the moment my team is observing from an office up on the 7th floor of the Cairo building using the 2.3 metre telescope at Siding Spring, hoping to add to our understanding of the cosmos a little, but I'm sorry to say the humidity is preventing us from working at the moment. Hopefully we'll start soon, and if I leave halfway through the lecture in a panic, it's because something's gone wrong at Siding Spring Observatory. Okay, so I'm going to talk about the expansion rate as the first of 3 parts of this lecture. Jeff mentioned that the expansion rate of the universe, of our expanding universe, is called or measured by the Hubble constant. And here's Edwin Hubble smoking his pipe. He was an astronomer at the Mount Wilson Observatory in the San Gabriel Mountains north of Los Angeles, and did his work on the expanding universe in the 1920s and 30s. I'll show you some of his results in just a moment. But what do we mean by the Hubble constant and the expanding universe? Well, the idea of uniform expansion is schematically very easy. Imagine you have a triangle, perhaps it's connecting 3 galaxies, and the one side of the triangle has dimension A. A little while later it expands to A plus a small increment. Well, the Hubble constant is defined as the time derivative of A divided by A itself. For those not happy with dA by dt, it's just the small increment in A divided by a small increment of time. So the triangle's got bigger, and this just measures how fast it's getting bigger. So Hubble's first data on the expanding universe, published in 1929, plots the redshift of galaxies, or the velocity of a galaxy relative to us, the observers, as a function of the distance away from us. The distance is measured in a unit called parsecs, which I'll explain in a moment, but a parsec is just 3 by 10 to the 18 centimetres, and the velocity is measured by taking the spectrum of the galaxy. You see that the lines are Doppler shifted, the effect that we all know about when a siren approaches and leaves, changing the frequency of the note of the siren. So that Doppler effect can be measured in galaxy spectra, and this was done at the turn of the 20th century. Hubble was the first, however, to measure velocity of galaxies and plot distances. He was really the first to have a reasonable shot at measuring galaxy distances. It's not obvious when you look at a galaxy whether it's near or far. When you resolve it into stars, which is what he did, it becomes a little bit easier. Well, by now you've seen that this is fairly ratty data as far as a correlation is concerned, but the more distant galaxies are certainly moving faster. Ignore, if you can read it, the fact that he's labelled his axes here kilometres, whereas he really means kilometres per second. Perhaps the referee didn't catch it. Perhaps it wasn't refereed. It was published in the Proceedings of the National Academy in the US. But astronomers have never been afraid to draw straight lines through raggy data. And the slope of that curve, the gradient of the graph, if you like, the change in velocity per change in distance, he measured to be 500 kilometers per second per megaparsec, and as we'll see, he was off by a factor of, off by almost an order of magnitude, entirely in his distance measurements, because the velocity measurements, oh, it's hard to make an error there. So I said I'd say what a parsec was, and it's an astronomical unit based on the concept of astronomical parallax. And here we are, 1 AU from the Sun. That's the Earth-Sun distance, known as the astronomical unit. And if a star that we want to know the distance of is so far away, 1 parsec away, that this angle here is 1 arcsecond, an arcsecond being a 60th part of an arc minute, being a 60th part of a degree. Okay, so quite a small angle. Well, that defines the distance of a parsec. That star is a parsec from us. So you might also note that if the star was 1,000 parsecs away from us, that angle would not be 1 arcsecond, it would be a milliarcsecond. Now we're really talking about small angles. And galaxies begin 1 megaparsec away, so the chance of measuring the distance of a galaxy by this technique, the parallax technique, where the angle up here becomes 1 microarcsecond, well, that won't happen until a spacecraft goes up that can do that, and the relevant spacecraft was cancelled some time ago. There are other ways of measuring distances for things that are further away, and many of you will have seen the Magellanic Clouds, the nearest galaxies to our own in the southern sky, and a supernova went off in the Large Magellanic Cloud. There it is, a very bright object in February 1987. I can remember it well because I was at the Parkes telescope, radio telescope, and the supernova went off, and the director threw us off the telescope so that supernova observers could take over. It was very annoying. But, of course, it was important. And so this actually provides a methodology for measuring the distance of the Large Magellanic Cloud. Because after the star had faded, and here's the star now, faded by 250 days, you'll probably say a supernova is an exploding star, and there's immediately an awful lot of light as the core of the star collapses and throws off its envelope, eventually to become a neutron star or a black hole. But a light pulse went out from the centre out to a pre-existing overdensity of material the star had previously thrown off. So just gas and stuff which had been thrown off by the star in its late stages of evolution before it exploded. And the light lit up this gas, ionized it, and it then emits some radiation. And so this gives us a distance measurement, in fact, because you know what this distance is in kilometres, because it's just the velocity of light times 250 days since the explosion. And so with the Hubble Space Telescope we were able to measure the angle on the sky that represented. So if you like, oops, wrong way. Going back to this diagram, it's possible, knowing the angle and knowing how large the object is in kilometres, the CT, then you can get the distance, which turned out to be 50 kiloparsecs, and we won't worry about the 18.5 parts. There are other ways of measuring galaxy distances, and these go back quite a long time as well. They are are Cepheid variable stars. A Cepheid variable star is quite a luminous star that is pulsating. It's unstable and it's getting 10% smaller and larger with a period of a week to a few weeks. These stars obey a relationship between the period of the oscillation, P in days here, and how bright they are. The long period ones are very bright, and the short period ones, 10 days here, are a good deal fainter. These brightness measurements here are on a logarithmic or magnitude scale, and we measure them at different wavelengths. This is in the visible wavelength, and this is in the infrared. So this provides a technique for measuring relative distances of galaxies. If you can find a galaxy where the stars at a given period are 100 times fainter than the ones of the same period in the Magellanic Clouds, then that galaxy is 10 times further away because of the inverse square law. So that's another good technique, but of course it does mean that you need to know the distance of the Large Magellanic Cloud to do it, as I said, the Supernova technique gave us the distance to the Large Magellanic Cloud. And we won't worry about that one. But the Key Project, the Hubble Space Telescope Key Project to measure the Hubble constant, which Jeff mentioned, had as a goal to measure the expansion rate, the Hubble constant, to 10% accuracy. Before we started this project, it was known to a factor of 2. In other words, we didn't know whether the Hubble constant was 50 kilometres per second per megaparsec, there's that gradient again, or 100 kilometres per second per megaparsec. And 10% accuracy was the goal, using the Hubble Space Telescope to measure galaxy distances using the Cepheid technique that I've just described. The team that we assembled to do this, which I think has gone off the bottom of the page, but no matter, consisted of the 3 people that Jeff mentioned, and a number of other astronomers, including, let's see, 1, 2, 3 Australians, plus myself. We didn't really get underway until the Hubble Space Telescope had been serviced. You may remember when it was launched in 1990, it was rapidly discovered that it had a aberrated mirror. In other words, the mirror had been ground to the wrong shape. But it was quickly realised that by inserting an additional small lens in the cameras, rather than bringing the telescope back to Earth and replacing the mirror, that just contact lenses, as they were described in the press, would fix that problem and give us the images that, being outside the turbulent Earth's atmosphere, would be as good as you could get. And so the astronauts did this in December 1993. They installed new instruments at the base of the telescope, and we were away. Is that the picture I thought it was going to be? There's some slides missing here. Anyway, I hope there's not too many missing. Pictures as good as this resolve galaxies into stars. So this is a galaxy that we obtained Cepheid variable stars in. The Cepheids are amongst the brightest stars, and they tend to be out in the blue-coloured regions of galaxies where star formation is recent and massive stars have formed. Massive stars don't last long, and so it's only in regions of recent star formation that you can see them. in a typical galaxy in this program, and we had some 20 galaxies that we searched for and found Cepheids in. We'd simply feed the CCD data, same thing as your digital camera produces, to a computer program, which perhaps we ought to go back, inputs this image, goes and finds all the stars simply as peaks in the light distribution, and then measures their brightness. Now, if you have a sequence of a dozen or so such observations, then you can find the stars that vary, and the stellar measurements are just put into a big database, and the database is then analysed to find the ones that vary. And when we plot the brightness of the star, brighter stars are higher on the y-axis here against the period, or phase if you like. You see the classic Cepheid light curve shape as the star is getting smaller, turns around, gets bigger and brighter, getting smaller and fainter again, and so on. And you can see Cepheids of different periods here, 60 days in this case, 55. You start off by guessing the period, and then you optimise the light curve until you get something which is smooth like that. 55 days, 53 days, and many more. Then we plotted the period luminosity relation, as we call it, brightness of the star against the period, and here you can see for the visible light and in infrared light that the mean line, at any rate, that you put through this data is quite well defined, and so you have the distance to that galaxy by the Large Magellan Cloud. And so we did lots and lots of galaxies, a dozen or more, plotting all the Cepheids in the period luminosity relation here, period and brightness. So you can see just how many we've got for each of these individual galaxies. So that sets us on our way to measuring the Hubble constant. The rest of the story I won't go into in detail, because in fact you can't see Cepheids out really far enough to measure the Hubble constant. Galaxies have turbulent velocities in the expanding universe as well, so you have to get a very long way out in order for those turbulent velocities to be negligible. So we use yet another distance indicator, which goes by the name of these two people, to measure out to a recession velocity of some 10,000 kilometres per second. We use a number of these secondary distance indicators, and I won't describe how they work, except this first one you just saw uses the fact that bigger galaxies rotate faster, but the results all lay within these error ellipses for the Hubble constant. Fortunately, none of them disagreed with one another, which would put us in a bit of strife. Remember I said that we needed the distance of the Large Magellanic Cloud as a starting distance in order to get that. That LMC distance, in spite of the supernova, isn't perfectly known, so that's why these error ellipses are sort of canted a little bit. If the distance of the Large Magellanic Cloud is actually 55 rather than 50 kiloparsecs, then the corresponding estimate of the Hubble constant is larger, and they will say the same thing. Nevertheless, the results are in good agreement, and further work since the Key Project has borne this out. Even better, more galaxies have been measured. Supernovae are tied into the calibration, and so while we got from the Key Project to 72 kilometres per second per megaparsec with an uncertainty of 10%, further work with the Hubble telescope by others has first of all agreed with our result, and secondly reduced the uncertainty, so that's running about 5% next piece of the story is the launch of the microwave background satellite WMAP, the Wilkinson microwave anisotropy probe, and that's an all-sky map of the microwave background radiation. Remember, we live in a universe that began with a Big Bang, and the Big Bang released a lot of photons. I suppose gamma rays at the time in the early universe, but as the universe expands, it cools, and those photons redshift, so they end up becoming radio waves in the microwave part of the spectrum, and we can still observe them today. Amazing. We can actually see photons that were created at the time of the Big Bang. And what we see looking around the sky from end to end and up and down is extremely smooth. You're saying, well, that doesn't look very smooth, but these fluctuations are a part in a million. It took a lot of work before the technology became so good that we could see a part in a million in the 3-degree blackbody radiation that characterizes those photons cooled and redshifted from the Big Bang. So now the question is, why the non-uniformity, and measure the non-uniformity, and this turns out to provide us with a measurement of the Hubble constant that's even better, because we can characterize the power or temperature fluctuations in millikelvins there, plotted vertically, against angular size, or as mathematicians prefer to put it, multipole. But here's your small angular, here's your medium-sized fluctuations, and here's your really small fluctuations, where we're talking about pieces of the sky, like a few degrees here, so this is half a degree, and the power half a degree. Anyway, the Hubble constant turns out to be measurable from where that peak of the power spectrum is. And I thought I wiped out that equation. I was certainly told to remove it. So, yeah. So ignore this, this equation. It's not meant to be a scary equation. It's possible I've loaded up a version of the presentation -1. Anyway, the fluctuations occur because a sound wave originating in the Big Bang, by the time that we get to see the microwave background radiation emitted, that is characterized by a certain distance here called the sound horizon. And so, as usual, if you divide that distance by the distance out to where the microwave background radiation is being scattered from, that defines a certain angle. And it's thus possible, just passing over this integral that one needs to do to get it, to obtain a measurement of the Hubble constant simply from that angle and that distance in the same way as parallax measurements are done. So I now want to move on to part 2 of this lecture. I said I'd talk about the expansion rate. I want to talk about dark matter. I want to talk about the acceleration of the universe, which of course is related to the expansion rate. And dark matter, amazingly enough, is much more abundant than the matter that we're made of, and indeed the matter that was being talked about in the last 2 weeks, the quarks and the protons and all of those good things. So, in fact, makes makes up 22% of the total energy density of the universe, whereas 4% is in atoms, and 74%, I'm going to come on to the third part of this lecture, is dark energy, which we also need to say something about. So what is dark matter? It's found in the outer parts of spiral galaxies, it's found in dwarf galaxies, and it's found in clusters of galaxies. Actually, it's everywhere, but we don't know what it is. It hasn't been detected in the laboratory yet, but presumably it is some form of particle that we yet have to identify. Perhaps a machine like the Large Hadron Collider will allow us to do this. There are a couple of ways of mapping the dark matter in the universe, and perhaps if we map the dark matter, we'll learn a little bit more about the nature of that dark matter. So the two techniques that I'm going to be talking about are known as weak lensing and peculiar velocities, and those are both technical terms, but they're easy to understand. Here is the method of mapping dark matter, which is called weak lensing, and it's the iconic picture of the weak lensing technique, because what you're looking at here is actually a cluster of galaxies. Well, it's easy to see that, in fact, the galaxies are clustered there, but it is a composite picture of X-ray gas, which is shown in red here, dark matter, which is shown in blue, and the regular luminous galaxies, which you can easily recognize. So maybe you're thinking now, how come I can see the dark matter? It's supposed to be dark, isn't it? Not blue. But what's happened here is that two clusters of galaxies have actually been attracted to each other and collided, and to some extent passed through one another. The hot gas, which every cluster of galaxies has in it, can't pass through itself, or can't pass through the opposite number coming in on the other side. It just collides and releases a large amount of X-rays, and that's the red gas there. But the dark matter, because it doesn't interact with the gas, has actually passed through and come out on the other side of the collision. Now you're saying, I'm still puzzled, you haven't told me how come I can see the dark matter. Well, it's rather clever. We can infer the presence of the dark matter because the more distant objects behind these clusters of galaxies have their images perturbed by the gravitational effect of the galaxies on the light that's passing near them. So it's a general relativistic effect. And we can actually look at those images and we can diagnose the presence of the dark matter even though the dark matter isn't emitting light. And so that analysis has been turned into a distribution, it's a pretty fuzzy distribution because the data are finite, and that shows us where the dark matter is. So that's one way of mapping the dark matter and perhaps learning more about it, and it's called the bullet cluster, possibly on these reasons. We can also simulate dark matter and its role in the universe in computers, because the dark matter, whatever it may be, interacts gravitationally, and so we can put particles gravitationally in a computer volume, and we can start off with a uniform distribution, and we can let it go in the expanding universe using the cosmological parameters such as the Hubble constant, which are now measured. And so we have a simulation of what the universe looks like at any time. Did that just fade? Anyway. And the universe turns out to consist in this simulation of filaments and strong concentrations, clusters there, and that whole structure, which is purely theoretical, can be compared with what we see when we measure the redshifts of galaxies And I have another missing slide there. Here it is. Anyway, when we make redshift maps of galaxies, their positions in space actually do show this filamentary structure. So we think we're onto the right sort of simulation for the universe. That's another slide where I had obliterated the equations. I'm always tempted to see if I can find a version of this. Yes, if I can find a version of this that has the equations obliterated. I do apologise. That's the one. Won't have to suffer through any more equations. And here is the slide that shows what, according to the Anglo-Australian Telescope deciding spring, and a survey that was completed some 2 years ago by Matthew Collis and collaborators of 200,000 galaxies using a technique employing fibre optics to get many galaxy redshifts all in the one exposure. And you can see this sort of filamentary structure. I'm sorry for the deep blue and black, not the ideal colour combination, but here are we, the observers, looking out as a function of redshift here, and here is an arc across the sky, and another arc. It's not so easy to show this on the slide, it's much better in 3 dimensions. Anyway, you can see the filamentary structure. So, one of the interesting things about the physics approach to dark matter, and physicists dearly wish to identify what dark matter is in terms of particles, is that you can put direct detection experiments in which you have a tank of something like half a ton of liquid xenon. That experiment hasn't quite been built yet, and you put it down in a mine, and the dark matter particles come through. All of the background particles are blocked, and they can be recorded, detected by neutrino interactions in the xenon. So this is an interesting approach, and we've got some nice mines in Australia. It might be well worth pursuing that sort of direct detection experiment locally. So what is the dark matter particle? We've seen a lot of the standard model, and you've been hearing a lot about it in the previous couple of lectures, and the quarks and the leptons and the 3 families and so on. Well, there are other models that challenge the standard model, and one of the functions of the Large Hadron Collider is to test whether the standard model is perfect or perhaps needs to be replaced by some variant of it. And there's a model with many more particles, so many more candidates for dark matter, called supersymmetry. You can see it sketched out here. A lot of people think that the Large Hadron Collider is well on its way to demolishing this model, but we do need a model that includes the particle or particles that make up dark matter, and we have to explain why they were produced in such abundance in the early universe. Okay, now I've got to my slide, which has been de-equationed. If we want to understand how to map dark matter using Bernoulli velocities, which I said is the other technique that we use, well, just imagine that we're in a place in the universe which is overdense in galaxies. More galaxies on average in this place here than there are outside it. And so we call this an overdensity, and we, the observers, are sitting out on the periphery looking into this overdensity. Well, we don't have to write down very complicated equations. They're the ones I blotted out. to discover that the velocity perturbation that is caused by us attracted by the overdensity is actually proportional to the overdensity. The proportionality constant is similar in the expanding universe cosmology to Newtonian cosmology, but it's just a slightly different value. So that approach to measuring velocities allows us to find out where the dark matter is and map it. To be precise, a peculiar velocity, V here, is defined as the redshift of the galaxy minus its Hubble expansion velocity. So I think I referred to it earlier as the turbulence of galaxy velocities. So to do this mapping project, we used an instrument called the 6-degree field spectrograph, and there's a telescope at Siding Spring which looks like this. It's actually just a clone of the one at Mount Palomar that did the Palomar Sky Survey in the 1950s, and so it was built to survey the southern sky at the time that the Anglo-Australian telescope was built. And we have a spectrograph on this telescope, which is the left part of the slide, and you can see these little button things pointing upwards. They actually house fibre optics, and so once again this is obtaining many galaxy redshifts at once, because you have to place the fibres precisely where the galaxies are going to be before you open the shutter on the telescope. And so we can get these peculiar velocities from the redshifts and distance measuring techniques, and we can compare them with predictions as to what the galaxy flow field, which is superposed on the Hubble flow, may look like. And I've taken a slice through the galaxies here, so X and Y axes here labelled in megaparsecs, so 100 megaparsecs out here. And we're at the centre of this distribution, and anywhere where you see white, that's an overdensity of galaxies, more galaxies than usual. Black is an underdensity. And you can see, according to prediction, which is simply gravity, anywhere there's a concentration of galaxies, the arrows are pointing inwards because the galaxy was attracted to that overdensity. Here's the biggest one here, which in the early days of this sort of experiment was called the Great Attractor, because we hadn't really understood what it was that was doing it. And you can see there's another monster concentration of galaxies in the southern hemisphere here. You can even see the prediction, the theory that galaxies will attempt to escape underdensities. Hard to observe though, because if there are no galaxies there, how are you going to measure the redshifts? Nevertheless, we completed the project with a large number of galaxies, and this enabled us to map the dark matter. One rather imaginative astronomer has produced this cartoon of the galaxies falling into an overdensity here, where we're supposed to be at the centre of this picture. I don't really like this picture. It's no way going to compare with the iconic bullet cluster picture of weak lensing, but you get the idea. The galaxies are falling into an overdensity, and that allows you to map the dark matter. So a Melbourne University student working with us, Christina Magoulis, has fitted the model to the data and finds that the model is really a pretty good fit for the data. Nevertheless, we want to go further and map the dark matter as completely as we possibly can. And for the next generation of this Mapping the Dark Matter project, we're going to use new facilities that have just been developed during the course of this development. Those of you who saw the press release about the sighting of the Square Kilometre Array, a next generation radio telescope in Western Australia, might have learned that although this huge project, the Square Kilometre Array, is many years in the future, we've already built a Pathfinder array, generously supported by the Australian government. And here are some of the Pathfinder telescopes that are in place. And this is going to be a tremendously powerful survey telescope that we can use for projects like, many projects, but projects like mapping the dark matter. And this is a new telescope at Siding Spring Observatory that I think is a result of the insurance